Tellurium. Tellurium is a chemical element with symbol Te and atomic number 52. It is a brittle, mildly toxic, rare, silver-white metalloid. Tellurium is chemically related to selenium and sulfur. It is occasionally found in native form as elemental crystals. Tellurium is far more common in the universe as a whole than on Earth. Its extreme rarity in the Earth's crust, comparable to that of platinum, is due partly to its high atomic number, but also to its formation of a volatile hydride which caused it to be lost to space as a gas during the hot nebular formation of the planet. Tellurium-bearing compounds were first discovered in 1782 in a gold mine in Zlatna, Romania by Austrian mineralogist Franz Joseph Müller von Reichenstein, although it was Martin Heinrich Klaproth who named the new element in 1798 after the Latin word for earth, tellus. Gold telluride minerals are the most notable natural gold compounds. However, they are not a commercially significant source of tellurium itself, which is normally extracted as a byproduct of copper and lead production. Commercially, the primary use of tellurium is copper and steel alloys, where it improves machinability. Applications in CDTE solar panels and semiconductors also consume a considerable portion of tellurium production. Tellurium has no biological function, although fungi can use it in place of sulfur and selenium in amino acids such as tellurocysteine and telluromethionine. In humans, tellurium is partly metabolized into dimethyl telluride, 2-Te, a gas with a garlic-like odor exhaled in the breath of victims of tellurium exposure or poisoning. Tellurium has two allotropes, crystalline and amorphous. When crystalline, tellurium is silvery white with a metallic luster. It is a brittle and easily pulverized metalloid. Amorphous tellurium is a black-brown powder prepared by precipitating it from a solution of tellurous acid or telluric acid 6. Tellurium is a semiconductor that shows a greater electrical conductivity in certain directions depending on atomic alignment. The conductivity increases slightly when exposed to light. When molten, tellurium is corrosive to copper, iron, and stainless steel. Of the chalcogens, tellurium has the highest melting and boiling points, at 722.66 K and 1261 K, respectively. Tellurium adopts a polymeric structure consisting of zigzag chains of Te atoms. This gray material resists oxidation by air and is not volatile. Naturally occurring tellurium has 8 isotopes. 6 of those isotopes, 120Te, 122Te, 123Te, 124Te, 125Te, and 126Te, are stable. The other two, 128Te and 130Te, have been found to be slightly radioactive, with extremely long half-lives, including 2.2 times 1024 years for 128Te. This is the longest known half-life among all radionuclides and is about 160 trillion times the age of the known universe. Stable isotopes comprise only 33.2% of naturally occurring tellurium. A further 30 artificial radioisotopes of tellurium are known, with atomic masses ranging from 105 to 142 and with half-lives of 19 days or less. Also, 17 nuclear isomers are known, with half-lives up to 154 days. Tellurium are among the lightest elements known to undergo alpha decay. The atomic mass of tellurium exceeds that of iodine, the next element in the periodic table. With an abundance in the Earth's crust comparable to that of platinum, tellurium is one of the rarest stable solid elements. In comparison, even the rarest of the stable lanthanides have crustal abundances of 500 g/kg. This rarity of tellurium in the Earth's crust is not a reflection of its cosmic abundance. Tellurium is more abundant than rubidium in the cosmos, though rubidium is 10,000 times more abundant in the Earth's crust. The rarity of tellurium on Earth is thought to be caused by conditions during the formation of the Earth, when the stable form of certain elements, in the absence of oxygen and water, was controlled by the reductive power of free hydrogen. Under this scenario, certain elements that form volatile hydrides, such as tellurium, were severely depleted through evaporation of these hydrides. Tellurium and selenium are the heavy elements most depleted by this process. Tellurium is sometimes found in its native form, but is more often found as the tellurides of gold such as calaverite and krennerite, petsite, Ag3Aute2, and sylvanite, Agote4. The city of Telluride, Colorado, was named in hope of a strike of gold telluride. Gold itself is usually found uncombined, but when found as a chemical compound, it is most often combined with tellurium. Although tellurium is found with gold more often than in uncombined form, it is found even more often combined as tellurides of more common metals. Natural tellurite and tellurate minerals also occur, formed by oxidation of tellurides near the Earth's surface. In contrast to selenium, tellurium does not usually replace sulfur in minerals because of the great difference in ion radii. Thus, many common sulfide minerals contain substantial quantities of selenium and only traces of tellurium. In the gold rush of 1893, miners in Kalgoorlie discarded a pyritic material as they searched for pure gold, and it was used to fill in potholes and build sidewalks. In 1896, that tailing was discovered to be calaverite, a telluride of gold, and it sparked a second gold rush that included mining the streets. Tellurium was discovered in the 18th century in a gold ore from the mines in Zlatna, near today's city of Alba Iulia, Romania. This ore was known as Faxabager Weiss's Blattriges Golderts or Antimonolisker Gold Kies, and according to Anton von Ruprecht, was Spice Glaskonig, containing native antimony. In 1782 Franz Joseph Müller von Reichenstein, who was then serving as the Austrian chief inspector of mines in Transylvania, concluded that the ore did not contain antimony but was bismuth sulfide. The following year, he reported that this was erroneous and that the ore contained mostly gold and an unknown metal very similar to antimony. After a thorough investigation that lasted 3 years and included more than 50 tests, Müller determined the specific gravity of the mineral and noted that when heated, the new metal gives off a white smoke with a radish-like odor, that it imparts a red color to sulfuric acid, and that when this solution is diluted with water, it has a black precipitate. Nevertheless, he was not able to identify this metal and gave it the names aurum paradoxium and metallum problematicum, because it did not exhibit the properties predicted for antimony. In 1789, a Hungarian scientist, Pál Kitábel, discovered the element independently in an ore from Deutsche Pilsen that had been regarded as argentiferous molybdenite, but later he gave the credit to Müller. In 1798, it was named by Martin Heinrich Klaproth, who had earlier isolated it from the mineral calaverite. The 1960s brought an increase in thermoelectric applications for tellurium, and in free machining steel alloys, which became the dominant use. The principal source of tellurium is from anode sludges from the electrolytic refining of blister copper. It is a component of dusts from blast furnace refining of lead. Treatment of 1,000 tons of copper ore typically yields 1 kilogram of tellurium. The anode sludges contain the selenides and tellurides of the noble metals in compounds with the formula M2Se or M2Te. At temperatures of 500 degrees C, the anode sludges are roasted with sodium carbonate under air. The metal ions are reduced to the metals, while the telluride is converted to sodium tellurite. Tellurites can be leached from the mixture with water and are normally present as hydrotellurites HDO3 in solution. Selenites are also formed during this process, but they can be separated by adding sulfuric acid. The hydrotellurites are converted into the insoluble tellurium dioxide while the selenites stay in solution. The metal is produced from the oxide either by electrolysis or by reacting the tellurium dioxide with sulfur dioxide in sulfuric acid. Commercial-grade tellurium is usually marketed as 200 mesh powder but is also available as slabs, ingots, sticks, or lumps. The year-end price for tellurium in 2000 was $14 per pound. In recent years, the tellurium price was driven up by increased demand and limited supply, reaching as high as $100 per pound in 2006. Despite the expectation that improved production methods will double production, the United States Department of Energy anticipates a supply shortfall of tellurium by 2025. Tellurium is produced mainly in the United States, Peru, Japan, and Canada. The British Geological Survey gives the following production numbers for 2009, United States 50T, Peru 7T, Japan 40T and Canada 16T. Tellurium belongs to the chalcogen family of elements on the periodic table, which also includes oxygen, sulfur, selenium, and polonium. Tellurium and selenium compounds are similar. Tellurium exhibits the oxidation states 2, +4, and +6, with +4 being most common. Reduction of Te metal produces the tellurides and polytellurides, 10-2. The 2 oxidation state is exhibited in binary compounds with many metals, such as zinc telluride, ZnTe, produced by heating tellurium with zinc. Decomposition of ZnTe with hydrochloric acid yields hydrogen telluride, a highly unstable analog of the other chalcogen hydrides, H2O, H2S and H2SE. H2Te is unstable, whereas salts of its conjugate base are stable. The +2 oxidation state is exhibited by the dihalides, TeCl2, TeBr2 and TeI2. The dihalides have not been obtained in pure form 274, although they are known decomposition products of the tetrahalides in organic solvents, and the derived tetrahalidolurates are well characterized. Where X is Cl, Br, or I. These anions are square planar in geometry. 281 polynuclear anionic species also exist, such as the dark brown Te2I26283 and the black Te4I214285. Fluorine forms 2 halides with tellurium, the mixed valence Te2F4 and TeF6. In the +6 oxidation state, the ATF5 structural group occurs in a number of compounds such as HOTEF5, B3, Xe2, Te4 and Te6. The square antiprismatic anion TeF28 is also attested. The other halogens do not form halides with tellurium in the +6 oxidation state, but only tetrahalides in the +4 state, and other lower halides. In the +4 oxidation state, halidolurate anions are known, such as TeCl26 and Te2Cl210. Halotellurium cations are also attested, including T+3, found in TeI3AsF6. Tellurium monoxide was first reported in 1883 as a black amorphous solid formed by the heat decomposition of TeSO3 in vacuum, disproportionating into tellurium dioxide, TeO2 and elemental tellurium upon heating. Since then, however, existence in the solid phase is doubted and in dispute. Although it is known as a vapor fragment, the black solid may be merely an equimolar mixture of elemental tellurium and tellurium dioxide. Tellurium dioxide is formed by heating tellurium in air, where it burns with a blue flame. Tellurium trioxide, beta-TeO3, is obtained by thermal decomposition of Te6. The other 2 forms of trioxide reported in the literature, the alpha and gamma forms, were found not to be true oxides of tellurium in the +6 oxidation state, but a mixture of Te4+, O and O2. Tellurium also exhibits mixed valence oxides, Te2O5 and Te4O9. The tellurium oxides and hydrated oxides form a series of acids, including tellurous acid, orthotelluric acid 6, and metatelluric acid N. The 2 forms of telluric acid form tellurate salts containing the TeO2,4 and TeO6,6 anions, respectively. Tellurous acid forms tellurite salts containing the anion TeO2,3. Other tellurium cations include TeF2+8, which consists of 2 fused tellurium rings, and the polymeric TeF2+7. When tellurium is treated with concentrated sulfuric acid, the result is a red solution of the zintal ion, Te2+4. The oxidation of tellurium by AsF5 in liquid SO2 produces the same square planar cation, in addition to the trigonal prismatic, yellow-orange Te4+6. Other tellurium zintal cations include the polymeric Te2+7 and the blue-black Te2+8, consisting of 2 fused 5-membered tellurium rings. The latter cation is formed by the reaction of tellurium with tungsten hexachloride. Interchalcogen cations also exist, such as Te2Se2+6 and Te2Se2+8. These are formed by oxidizing mixtures of tellurium and selenium with AsF5 or SbF5. Tellurium does not readily form analogues of alcohols and thiols, with the functional group Te, that are called tellurols. The Te functional group is also attributed using the prefix telanyl. Like H2Te, these species are unstable with respect to loss of hydrogen. Tellurethers are more stable, as are telluroxides. The largest consumer of tellurium is metallurgy in iron, stainless steel, copper, and lead alloys. The addition to steel and copper produces an alloy more machinable than otherwise. It is alloyed into cast iron for promoting chill for spectroscopy, where the presence of electrically conductive free graphite tends to interfere with spark emission testing results. In lead, tellurium improves strength and durability, and decreases the corrosive action of sulfuric acid. Tellurium is used in cadmium telluride solar panels. National Renewable Energy Laboratory lab tests of tellurium demonstrated some of the greatest efficiencies for solar cell electric power generators. Massive commercial production of CDTE solar panels by First Solar in recent years has significantly increased tellurium demand. Replacing some of the cadmium in CDTE by zinc, producing Te, produces a solid-state X-ray detector, providing an alternative to single-use film badges. Infrared-sensitive semiconductor material is formed by alloying tellurium with cadmium and mercury to form mercury-cadmium telluride. Organotellurium compounds such as dimethyl telluride, diethyl telluride, diisopropyl telluride, diallyl telluride, and methyl-allyl telluride are precursors for synthesizing metal organic vapor phase epitaxy growth of 2,6-compound semiconductors. Diisopropyl telluride is the preferred precursor for low-temperature growth of CDHGTE by MOVP. The greatest purity metal organics of both selenium and tellurium are used in these processes. The compounds for semiconductor industry and are prepared by adduct purification. Tellurium, as tellurium suboxide, is used in the media layer of rewritable optical discs, including rewritable compact discs, rewritable digital video discs, and rewritable Blu-ray discs. Tellurium dioxide is used to create acousto-optic modulators for confocal microscopy. Tellurium is used in the new phase change memory chips developed by Intel. Bismuth telluride and lead telluride are working elements of thermoelectric devices. Lead telluride is used in far-infrared detectors. Tellurium has no known biological function, although fungi can incorporate it in place of sulfur and selenium into amino acids such as tellurocysteine and telluromethionine. Organisms have shown a highly variable tolerance to tellurium compounds. Many bacteria, such as Pseudomonas aeruginosa, take up telluride and reduce it to elemental tellurium, which accumulates and causes a characteristic and often dramatic darkening of cells. In yeast, this reduction is mediated by the sulfate assimilation pathway. Tellurium accumulation seems to account for a major part of the toxicity effects. Many organisms also metabolize tellurium partly to form dimethyl telluride, although dimethyl ditelluride is also formed by some species. Dimethyl telluride has been observed in hot springs at very low concentrations. Tellurium and tellurium compounds are considered to be mildly toxic and need to be handled with care, although acute poisoning is rare. Tellurium poisoning is particularly difficult to treat as many chelation agents used in the treatment of metal poisoning will increase the toxicity of tellurium. Tellurium is not reported to be carcinogenic. Humans exposed to as little as 0.01 mg/m3 or less in air exude a foul garlic-like odor known as tellurium breath. This is caused by the body converting tellurium from any oxidation state to dimethyl telluride, 2Te. This is a volatile compound with a pungent garlic-like smell. Even though the metabolic pathways of tellurium are not known, it is generally assumed that they resemble those of the more extensively studied selenium because the final methylated metabolic products of the two elements are similar. People can be exposed to tellurium in the workplace by inhalation, ingestion, skin contact, and eye contact. The Occupational Safety and Health Administration limits tellurium exposure in the workplace to 0.1 mg/m3 over an 8-hour workday. The National Institute for Occupational Safety and Health has set the recommended exposure limit at 0.1 mg/m3 over an 8-hour workday. In concentrations of 25 mg/m3, tellurium is immediately dangerous to life and health.